Hello everyone, I'm Chaoyi from National University of Singapore. Today I will present Libra, a system for serving LM workloads under with unbalanced dynamic nature. This is a joint work with collaborators at USTC and UC Berkeley. Let me do a quick refresher on LM inference. Every LM request goes through two phases. One is prefill phases. It consumes the entire prompt in one forward pass. And we measure its responsiveness as a TTFT. And also prefill is a compute-bound workload. It's very easy to saturate GPU metric units. Then is the decode phase. Decode phase reuse the carry cache generated from the prefill pass and emit token one by one. We measure its smoothness as the time per output token, TPOT. Decode is a memory bound, different with the prefill phase. It's usually limited by the GBM bandwidth, not compute. So as we introduce, prefill and decode, they use different metrics instead of one unified matrix. They have different SO. This is a focus of the existing inference framework. Okay, let me introduce the two popular designs in today's world. On the left is the chunk prefill. On such serve, first introduce these concepts. The timeline shows how it works. Prefill chunks. Prefill chunk enter with the decode tokens. The GPU, both prefill and decode stays in one GPU. So its advantage is it has a very high utilization. However, the prefill decoder will interfere each other, so it will lead to very high tail latency for decode phases. On the right, this serve pioneer PD disaggregation. It separates prefill and decode into different GPUs using high-end network like IDMA to connect both GPU tools. The latency is very good for latency, decoding latency. However, the prefill decode ratio is a key issue. Usually, it's fixed at the deployment. If the ratio is not configured very well, it will lead to some idles for GPUs. For example, for decode-heavy tasks, it's very easy for prefill GPU to stay idle. Okay, both architectures implicitly assume workload is roughly stable. However, real production traits tell a different story. We showcase two representative workloads in real production. The top trace is edge code. Blue is prompt length. Orange is output length. The prompts for this workload, prompts are very long. Outputs are tiny. So it's considered a prefill-heavy workload. However, for our second workload is burst GPT, real triple trace. Notice the wild wings. The prompt output values flip between the decode-heavy and the prefill-dominant period, sometimes with minutes. The green line marks a perfect balanced workload output length would look like. You can see the real traffic must never sit on it. Let me make this concrete with two examples. Imagine a use case 3 textbooks as for a brief summary. That's massive prefill-heavy task. The prefill GPU is overloaded while the decode GPU sits nearly idle. Now flip it. For example, write me a 5,000 word story. It's a very tiny prompt. However, it will lead to a very long output. So in this case, code is now the bottleneck. The prefill is idle. Whichever way you provision, you will waste a certain amount of hardware during the serving. So in production, both strip call occur with the same hour. To measure those two methods quantitatively, we run control benchmarks on 3 workload shapes. Prefill heavy with 8,000 prompts and 32 output tokens, and balanced at 2,512. Decode heavy at 1,400. Both prompt output lengths are extracted from the chatbot. burst GPT. Sorry. Look at the prefill-heavy column on left. Disaggregation gives you a very clean 100% SLO attainment, but only at 0.83 RPS with one GPUs, because one GPU is basically idle. Collocations push the throughput to a very high of 1.49 requests per second, but the SLO attainment collapsed to 1.7. If the chunk size is not configured very well, completely unstable in production. The middle column shows a similar trade-off, but in a mild form. The right column shows is again the collocation still wins throughput. The disaggregation wins in SLO attainment, but the SLO gap narrows because decode heavy for decode heavy workloads, there is less preferring jamming the queue. Across all three collocation wins throughputs, while disaggregation wins reliability. No static choice deliverables. We need something adaptive, and this motivates the Libra design. Here we call for a paradigm shift. Today's systems force you to split at a prompt boundary, or collocation doesn't split at all. So both of them can be considered as a request split strategy from this view. So here Libra introduced a flexible partitioning and scheduling. FPS for short. FPS lets you split requests at any token position. We show two cases. Case one on the right, we can if a prefill is very long, we can split within the prefill. We can prefill, and the first micro request we mark R alpha can cover a partial prefill, and the R beta covers the remaining prefill plus the entire decode. As for the case two, where it's a decode heavy, we split at the decode. Now alpha takes all prefill plus some decode tokens. R beta handles remaining decode. Let's SU offload the decode work onto a GPU that otherwise sit idle after prefill. Here is a how-to level architecture, fixed scale, a global schedule. We have a global schedule at top, sit in front of the GPU tools. For every incoming request, it consults a lightweight performance predict picks split point and runs the resulting micro request to GPU instance. Below it, every GPU runs identical local scheduler. The local scheduler composes SLO-aware batches from micro requests it receives. There's no prefill GPU here. There's no prefill GPU and the decode GPU in our designs. Every instance is interchangeable. Carry cache flows between instances after split. The first GPU shifts its carry cache state to the second, so decoder can continue seamlessly. We will cover the optimization in the subsequent slides. The next 3 sections will dive into each component: global scheduling, local batching strategy, and the carry transfer optimization in order. Okay, let's first introduce the global scheduler. The global scheduler decides where to split each request. The intuition of our design comes from a queuing theory. The end-to-end result is determined by whichever GPU is slowest. To build the picture, we take a concrete example, a request with 1,024 token prompt, roughly 1,076 decode tokens, about 2,100 tokens in total. Now imagine we're sweeping the split point across the entire request from left to right. Early in prefill, always do a decode. Ask what happens throughput on each view. Let's first show the GPU 1 alone as we push a split point later from left to right, meaning the GPU 1 takes more of those 2,100 tokens per request. Its throughput drops. This is because GPU 1 takes most of the prefill tasks, and the prefill is a compute-heavy workload. Now overlay the GPU 2, the opposite trend. As split moves later, the less of requests lands on the GPU 2, so its throughput climbs. Where two curves cross is the only point when near GPUs stuffs are the end-to-end throughput is the minimum of the two, as shown in the green dashed line. Whichever GPU is passive system, so the per request optimal is unique. It's sit exactly at the crossover, where two stages produce at the same rate. Anywhere else, one GPU finishes early on idles. Now let's see where today's system stands on this curve and how Libra finds the peak. This serve is forced to cut at the prompt boundary, token at 124, landing at 1 IPS. In contrast, Libra finds equilibrium at the token 1058, where two GPUs meet. It achieves around 2.5 requests per second, a nearly 50% gain on this single request. To find this equilibrium point, we propose a solver to solve this problem. It's a boundary binary search on this partition ratio. It starts from the PD disaggregation point at the end of prompt, and predicts each GPU's execution time based on the metrics we collected, reusing the cumulative clocks from the previous request. So for every new request, we just calculate the delta corresponding to this request runtime. And we bisect the file until the two GPUs times converge within the epsilon. Also, we limited the entire search under 6 iterations. This is the experience number. The results lands within 1%. Then the two micro requests are routed. After speed, the two micro requests are routed by least load policy with round robin strategy. Once micro requests arrive at GPU, the local scheduler decides what goes on each batch. The chart shows the latency on y-axis as we add more decode requests to a batch. The blue curve is a batch with a light prefill load, 500 tokens. The dashed gray curve is a heavy prefill, nearly 2,000 tokens. As we can see from this figure, for a heavy prefill, like the gray one, no matter we cannot add any decode request to this batch. And for the blue one, we can add some decode tokens to this batch, around 30 tokens before it breaches the SO latency. This surface schedule has to navigate. Then if static batching, they didn't care about what kind of requests within this batch. They only care about the entire batch size. So our local schedule it cares about the batch composition. It will tune the batch size, prefill to decode ratio, and the decode context jointly. So in this way, it can adapt every batch under SO constraints. The last piece is the carry transfer. The traditional carry cache is start at the end of the prompt prefilling. However, since we have transformed the request into several chunks. So here we stream the KV in pieces. Every prefill chunk ships as long as it's done. While server 1 moves on to the next chunk, the server 2 is already pulling in the previous one. So a transfer overlaps compute, making 94% of transfer being overlapped. Okay, now let's quickly introduce our experimental setup. We use Chen family model ranging from 14 billion to 72 billion model. We write 4 workloads. We evaluate the VM in 2 modes. One is chunk prefill, the other is PD disaggregation. We measure goodput serving capacity under SO constraints. As we can see, the Libra lists in almost configurations. It brings up to 91% over colocation and 61% over PD disaggregations. And as for the serving capacity, that's the maximum sustained QPS while still meeting SLO. Libra delivers up to 2.37 times over PD collocation, up to 1.37 times over PD disaggregations. And we also show the Libra performance under a hybrid workload, burst GPT and Azure workload. It still brings us very promising performance gains, up to 60% over PD collocation and 50% over disaggregation. We also showcase how Libra is applied in COT. For example, for syncing tokens, it's invisible for users. So maybe we can set a different SO for syncing tokens. We can do some, we can lose the SO constraint for syncing tokens. In this way, we can Libra can allow more split. For example, we can do 3 split for this request. Further bring 12% performance gains, up to 41% over PD disaggregation. Okay, to wrap up, we propose a flexible request partitioning and scheduling strategy, and based on that, we build entire systems. In this way, finally, we hope we can, no matter what kind of workloads, we can still improve the GPU utilization. Thank you for everyone. I'm happy to take any questions.